There were a couple other problems, geometry problems, that we were able to solve using integrals. So let's translate those into parametric curves. For example, let's find the arc length of one loop of this spiral. When I say one loop, what I really mean is for t values from 0 to 2 pi. For this spiral, right? So we're going from t equals 0, which happens to be at the origin for this spiral. We're going around once like this. You can see that the later loops have different arc length, much longer arc length. So we're finding just this first loop. Okay, well, for arc length, right, when we figured out arc length, all we did was we integrated ds. And if you remember ds, we had two different ways of writing it. One was the square root of 1 plus dy dx squared dx. And the other way of writing it was dx dy squared plus 1 dy. But both of these came from dx squared plus dy squared. Or sorry, square root of dx squared plus dy squared. If we're talking about a parametric curve, this last way of writing it seems best because we can rewrite dx and dy in terms of dt. So when we do that, right, dx is dx dt, so that's squared, plus, and then dy is dy dt times dt, so that's squared, so square root of the whole thing. And then if you multiply all this stuff out and simplify it, you get the square root of dx dt squared plus dy dt squared. And the dt, when you move it outside of the square root, the dt turns out positive. So to find the arc length of a parametric curve, we can use this third form of ds down here. So we'll integrate this big messy square root, dt. Our t values are going to be from 0 to 2 pi, because that's what it says up here. Okay, now we need to calculate some derivatives. So the derivative of x with respect to t, we have to do the product rule. So we get cosine t minus t sine t. And then for dy dt, we have to do the product rule again. We get sine t plus t cosine t. Okay, so now we can put this all into our integral. So cosine t minus t sine t squared. I'm writing small because I'm trying to fit it all in. So sine t plus t cosine t squared. Now we're going to have to multiply all this stuff out. So this is going to get worse before it gets better. But let's keep our fingers crossed for something that we can integrate. Okay, so squaring the first piece, we're going to get cosine squared t minus twice the cross term, so 2 times t sine t cosine t, and then plus the second bit squared, so t squared plus, no, t squared times sine squared t. So that's this first part squared. Now for the second part, we get sine squared t plus 2t sine t cosine t plus this last bit squared, so it's t squared cosine squared t dt. Okay, now simplify this. So integral from 0 to 2 pi. Cosine squared plus sine squared is 1. These big middle terms cancel, which is nice. And then these last terms, right, if you factor out the t squared, they turn into t squared times cosine squared t plus sine squared t. And the cosine squared plus sine squared is 1, so we just get plus t squared. Okay. Now, so now we need to evaluate this integral. Well, I don't know off the top of my head what an antiderivative for this is, but this seems like the sort of thing where we should use a trigonometric substitution, right? When we have a sum of squares, that's usually when we use tangent. So let's use t equals tangent theta. So dt is secant squared theta d theta. So this is integral from 0 to, this 2 pi is a t value, so let me remind myself that that's a t value. Square root of 1 plus tangent squared theta times dt, which is secant squared theta d theta. And then when we do all our trig identity business, this square root of 1 plus tangent squared is secant theta. All right, so for this whole mess, we get the integral from 0 to 2 pi. Again, these are t values of secant cubed theta. And secant cubed, I don't remember the integral of secant cubed, but I do remember that that's one of those messy ones where you have to do integration by parts once and then use a trig identity to, and then solve a big equation for the integral that you want. So I know that I could do that, but I also know that we have worked this out before, so I'm just going to look this one up. Okay, so this is 1/2 secant theta tangent theta plus 1/2 natural log secant theta plus tangent theta. Okay, and we're going from t equals 0 to t equals 2 pi. All right. Now we need to get back to our t's. So, right, if we have theta here, tangent theta is t, so we need a t here and a 1 there. So we need square root t squared plus 1 here. So in terms of t, secant theta is square root t squared plus 1. Tangent theta is just t plus 1/2 natural log absolute value secant theta, which is square root of t squared plus 1 plus t. And this is all from t equals 0 to t equals 2 pi. So now I can just plug in my bounds, finally. So let's factor out that 1/2. Okay, so when I plug in 2 pi, I get square root of 4 pi squared plus 1 times t, so times 2 pi, plus natural log square root 4 pi squared plus 1 plus 2 pi. And then when I plug in t, I think everything's going to turn out to be 0. Yeah, we get 0 plus natural log of 0. So yeah, 0. So this is the arc length of one loop of that spiral. All right, so the integral was a bit nasty, but right, the thing that I'd really like you to take from this example is how we started with a geometric problem we knew how to solve, right? To get the arc length, you integrate, we just integrate ds, And ds we had in terms of x and y. When we had ds in terms of x and y, we can rewrite it in terms of t when you have a parametric curve. Let's look at one more example of that. Let's find the surface area swept out by this curve when we rotate it about the x-axis. So forget for a second that this is a parametric curve. If we have a surface area and we're sweeping around the x-axis, so surface area swept out is an integral of the circumference that you go around, which is 2 pi times the radius, times the bit of arc length that you are sweeping, right? So since we have some curve, so here's our bit of arc length, we're rotating about the x-axis like this. That means the radius here is y. So for this example, this is the integral of 2 pi y ds. And then we choose whatever expression is appropriate for ds. And since we have a parametric curve, the most straightforward way to write ds is the square root of dx dt squared plus dy dt squared dt. Right, so this entire chunk here is ds. So you can see that we are finding this surface area with a parametric curve, but we actually aren't using any new ideas. It's still the same formula for surface area. We're just writing it in terms of the parameter instead of in terms of x and y. Oh, and I've written t everywhere, but I guess I should be writing theta since our parameter is theta in this example. Okay, and since theta is going from 0 to a pi over 2, there should be a less than or equal to theta like this. Our bounds are going to be from 0 to pi over 2. Okay, so now let's write everything in terms of theta. Dx dy, dx d theta, right? Take the derivative of our x coordinate function. It's 3 cosine squared theta with a minus times sine theta. Careful about your chain rule. And then dy d theta is 3 sine squared theta times cosine theta. All right, now we can put everything into our integral here. So integral from 0 to pi over 2 pi times y, but y was sine cubed theta times the square root of, so now we need to square dx d theta, so that's going to give us 9 cosine to the 4th sine squared theta plus, and then dy d theta squared, so that's 9 sine to the 4th theta cosine squared theta d theta. Okay, integral from 0 to pi over 2 pi. I feel like I want to start by simplifying the stuff in the square root. So let's leave this sine cubed theta alone just for now. There's a lot in common inside the square root, so let's factor out the common stuff. Let's see, we have a 9 in common, and both of these have a sine squared, and both of them also have a cosine squared. And when we factored out the common factors from this first piece, the stuff that's left over is cosine squared theta, and from the second piece, the stuff that's left over is sine squared theta. Oh, and that's good because sine squared plus cosine squared is 1, so all this stuff in parentheses is just 1. All right, so now we have integral from 0 to pi over 2 pi times sine cubed theta. And actually, everything inside this square root is a perfect square, so now we can take the square root. We get 3 sine theta cosine theta d theta. And now, so integral, let's see, we have 2 pi and 3, so that's 6 pi. We can move that outside. integral from 0 to pi over 2. So now we have sine to the 4th theta times cosine theta d theta, and now this is set up for u substitution. Now we can say that u is sine theta, du is cosine theta d theta, and we get 6 pi times the integral. So when theta is 0, sine theta is 0, and when theta is pi over 2, sine theta is 1. So u to the 4th du. So 6 pi times 1 over 5 u to the 5th from 0 to 1. So this is 6/5 times pi. So the surface area swept out by that graph is 6/5 pi.